Okay, hello. This is Dallin Havens with the Math 420 class. We're going to do quiz 7, which is a linear DE using matrices. So we're given the three equations: dx dt equals 6y, dy dt equals x plus z, and dz dt equals x plus y. And we can put this into a matrix form, which will give us the equation k vector a minus lambda I. Okay, so we're going to start with A. A in this case will be 0x, 6y, and 0 for z, 1x, 0y, and 1z, 1x, 1y, and 0z. So you can see along our main diagonal we're given only zeros. So in this case, A minus lambda I will be this matrix: negative lambda, 6, 0, 1, negative lambda, 1, and 1, 1, negative lambda. Now to find where this matrix equals our zeros, which is where eventually we'll find our k's, we're going to find where a minus lambda I, the determinant of that, equals 0. So we'll find the determinant of this. Okay, so in this case I think I'm going to just use the top row, which is going to be plus minus plus, and the determinant will end up being negative lambda, and then we'll cross out the row and column that element is in. So it will be the diagonal there, and then 1, 1. So that, the determinant of that, minus 6 times 1, 1, 1, negative lambda. So you can see we crossed out the row that 6 is in and the column that 6 is in to get 1, 1, 1, negative lambda, and then plus 0, and the determinant of that goes to 0, so we won't worry about it. Okay, so we're going to multiply those and subtract there. So that's going to be lambda squared minus 1 times our negative lambda, minus 6 times negative lambda minus 1. Okay, so we can factor out a negative there, and those will all turn into positive. Let's distribute this and set it equal to 0. So we have negative lambda cubed plus lambda plus 6 lambda plus 6. And we can end up with an equation that goes negative lambda cubed plus 7 lambda plus 6. Now that looks like it would factor if this was squared, but in this case it won't, so we'll have to, I think, use synthetic division. So we have negative 1 for our first coefficient and 6. So let's just say, using our rational roots theorem, that's 6 on the top, 3, 2, and 1. And just on the bottom, that's plus or minus 1. So these are all the combinations of roots that we can have. In this case, let's say 3 might be one of our roots. So let's have negative 1 for the third term, 0 for the second, 7 for the lambda to the first term, and 6 for the lambda to the 0th term. Okay, let's start our synthetic division. Drop the negative 1 times 3 is negative 3. Add those. And then we get 9 here. Negative 9, actually. Here we have negative 2. 3 times negative 2 is negative 6, so we're left with a remainder of 0. We got lucky, and that gives us lambda minus 3 times negative lambda squared minus 3 lambda minus 2. Okay, so these two polynomials, or yeah, I believe that this is a polynomial as well. These FOIL out and multiply to become the original equation here, r lambda plus negative lambda cubed plus 7 lambda plus 6. Okay, and then let's actually set this equal to 0 again. So we know that one of our lambdas is going to be 3. Since lambda minus 3 equals 0, we'll add 3 to both sides like that. So one of our lambdas is going to be 3. We'll put that over there. Alright, so factoring out this polynomial, we'll have one of the lambdas be negative in the front here. And then I believe that will leave us with 1 and lambda plus 2. Let's see, and then we'll double check that by foiling it. Squared, negative first, and then outer, negative 2 lambda, inner, oops, negative 1 lambda. Oh, it's a bad eraser. That's a 1 lambda minus 2. Okay, so it does work. And we get back negative lambda squared minus 3 lambda minus 2. So that's the correct factorization of that. So we have lambda minus 3, negative lambda minus 1, and then lambda plus 2, all equal 0. Okay, we already found our 3, so let's set negative lambda minus 1 equal to 0, which will be plus 1, and then we'll get lambda equals negative 1, and lambda equals negative 2 as well. So negative 1 and negative 2 for our lambdas. So we're going to take these values and we're going to plug them back in to our a minus lambda I, and that will give us a system of equations to solve for our k vectors. We're going to get 3 of those. So let's do that. Let's start with the positive, lambda equals 3. Okay, so that will give us negative 3, 6, 0, 1, negative 3, 1, 1, 1, negative 3. Okay. And these all equal the 0 vector. Okay, since we're working with a homogeneous equation. Alright, so let's do a simple one. I think the second row looks pretty good. So we'll go 1 k1 minus 3 k2 plus k3 equals 0. And the third row also looks pretty good. I think we can subtract them to eliminate k1. K2 minus 3, k3 equals 0. Okay, we're going to subtract this row to eliminate k1. So that gives us 0 there. Negative 3 minus 1 is negative 4 k2. And 1 minus negative 3 is going to be plus 4 k3. 0 minus 0 is 0. So now we have a k2 and k3 formula. Okay, let's take that and let's see where we can use it. So we have the first or the second and the third formula. Let's just start saying, oh, this one we can actually use to say 4k3 equals 4k2, and that will tell us that k3 equals k2. So no matter what, k3 and k2 are going to be the same. And then let's find a way to compare that to our k1. So we have negative 3k1 plus 6 k2 equals 0. Okay, so if k2 can be replaced for k3, we'll just find a way to relate k1 with both of these. So it looks like 6k2 equals 3k1, and we'll divide them by 3 to get them down to a, sorry, I got off the camera again. Let's make some room here. Okay, so here I just used our first row to make this equation, and then we're going to relate k1 to our k2 and k3. So we divided by 3 there, that becomes a 2. So k1 equals 2, k2 equals, and since k3 equals k2, we'll say 2k3 as well. So if I say k2 and k3 are 1, then k2 or k1 is going to be 2. So let's say our first k vector is going to be 2, 1, and 1. Alright, and these numbers are arbitrary. So we just try to find a number where it looks nice, and usually we want to have a 1 in one of those. Okay, so let's go to the next page, make some more room, and this time we're going to do lambda equals -1, which is one of our roots. Okay, let's make a new a minus lambda I vector using -1. So we're going to go -1, 6, 0, 1, -1, 1, and 1, 1, -1. Okay, so these are also going to give us another k2 vector. And you can see, by the way, with our roots for lambda, these eigenvalues are going to give us real and distinct eigenvalues. So we're going to be using the characteristic equation of, I'll just put it way down here, it's kind of out of our way. Our characteristic equation is going to be y equals the k vector e to the lambda t, I believe. Yeah, since we're doing dx dt, dy dt, and dz dt. Okay, so we'll have 3 of these type of looking characteristic equations. Okay, so let's find our k2 vector. The first row looks pretty good since one of them is already 0. Let's go -1 k1 plus 6 k2 equals 0. And remember, we're setting this equal to a 0 vector over here. Alright, so 6k2 equals k1, and we can't get k1 any more simplified. So in this case, if k2 is 1, k1 equals 6. Okay, so we'll just say k1 equals 1, k2 equals 6. Okay, let's find a way to relate those two to k3. And in this case, k3 is just a single value, so let's try that. Alright, 1k1 minus k2 plus k3 equals 0. Alright, if k1 is 1 and k2 is 6, then k3 is going to be 5. Alright, so it looks like that's sort of the least common denominator we can have, where one of them is a 1. So we kind of got lucky. Sometimes if you just plug in 1 for any of them, another one will end up being a fraction. But in this case, k1 being 1 is fine. So this is 6 and that's 5. Okay, and our last eigenvalue, which is -2, is going to give us -2, 6, 0, 1, -2, 1, and 1, 1, -2 equals this 0 vector. Okay, let's try the top row again. -2 k1 plus 6 k2 equals 0. And then we end up with 6 k2 equals 2 k1. And we can divide both of these by 2 and end up with k1 equals 3 k2. That's kind of nice. So if k2 is 1, k1 is 3. And let's find out how that relates to our k3. We'll do the same thing we did last time. So 1 k1 minus 2 k2 plus k3 equals 0. If k2 is 1 and k1 is 3, then what is k3? So 3 minus 2, that's 1. Our k1, or k3, ends up being -1, which is fine. So we'll say k3 vector equals our k1, 3, 1, and -1. Alright, so we have our 3k eigenvectors. I'll just list them out here. k1 equals 2, 1, 1. k2 equals 1, 6, 5. And k3 equals 3, 1, and negative 1. Alright, now we're going to pair those up with their eigenvalues in the characteristic equation, and adding those together will give us our general solution in matrix form. So let's try that. Okay, so for our general solution, we're going to say the x vector equals, and then we're going to use this characteristic equation for matrices. So for this eigenvector, our eigenvalue was 3. So I'll just put a 1 and 2 and 3 there. So for this eigenvector, our eigenvalue, you can see up here, was negative 1. Sorry for the glare from the sun. So that one's negative 1, and for this eigenvector, our eigenvalue was negative 2. Okay, so our general solution is going to be 2, 1, 1 there, e to the 3t, plus 1, 6, 5, e to the negative t, 3, 1, negative 1, e to the negative 2t. And some textbooks and others sometimes distribute this to say, you know, this vector is 2e to the 3t, 1e to the 3t, 1e to the 3t, but in this case we'll keep our k vectors separate, and we'll say, oh, we almost forgot. So these ones also have some constants for when we're plugging in initial values. Since we kind of used arbitrary values for our k vectors, these will have some constant that can multiply in to make it more definite. But in any case, this is our general solution. We're going to box that and turn it in. And there we go. That's how to solve a linear system of equations using matrix form. Thanks. Bye.